Oh, Aryan, you made it. I was not sure if everyone liked it or not. I just forwarded it.
This is the participant microphone. So if you have a question or want a comment heard, just like speak to it like this, and then Shajesh has this microphone. Yeah, I had microphone.
Advantages to having younger people do this.
You can't. You have this big. It's a talking stick.
One of this is the talking, and the one the speak. Oh yeah, this is the one. This came on Friday. Yeah, this is the new one.
Samara came with this swinging stick.
The tripod is mine.
Oh, yeah,
I have the tripod and the microphones because I record my class lectures.
This is a streaming camera, so it has a battery attached, Wi-Fi, everything. So in principle, it should just work out of the box.
How long the battery working?
More than 3 hours, I think. But the challenge is when you really use that, the phase lag is more than a minute or maybe 30 seconds more. So we are not using that. We are really connecting a wire to that to the computer. So.
Yeah, like what is this?
It's 10 times.
2K. Okay.
30 frames.
Oh, the. Don't even know the numbers that you
I
guys
think I
talk
might
about.
actually get myself one of these. This is really nice, and I don't think it would be good.
Yeah, let me know if you guys learn something creative. And we want to attach this whenever we are working in other rooms. It should be easy to attach on the wall, right? That's so without violating the union rules.
Mm-hmm.
You guys.
The poor math is rich.
We have a TV, but we don't have a camera.
We have one TV here. Can we that one? Oh yeah, across the wall.
Sorry.
So before we proceed, can we talk about what's going to happen in the summer? Because I don't have any results. How we want to do this summer?
Are we going to decide in summer?
Yeah, I'm just surprised at how much interest there is for this. So I don't know. Yeah.
Okay. Wow.
No, really. I mean, when we usually run, I mean,
We started with 4 people.
Yeah.
And now we have 8 regular participants. Probably move to 9, 10, 11. Just keep going. Eventually, we'll have to start. Get a crowd 450. Get a crowd from this.
We sort of semi-decided that we'll start with still on Thursday.
And now we have the camera, people can attend online. But I will encourage people from here to be. It's nice to be.
Well, I am graduating, so I won't be able to. So I would have to attend online. I don't think I don't have an interest, so like I won't be able to. Yeah.
No, that's the whole point that we can use this. But I would say, I think all of us agree that coming here is better than.
Yeah, I
attending
definitely
online.
agree to that,
Yeah.
but
otherwise,
it's not affordable.
Sure,
for me.
sure.
I can upload the Zoom link to the website, so that's easy to access.
I hope potpourri.
I can check it at some point.
Yeah, it should be continuously working. There is one thing I wanted to inform you, right? I heard from the university leadership, like our department chair just writes an email afterwards. Echo 360 that you use for saving the videos, they are planning to discontinue. That's just for information.
So we suggest
That was just one line saying that they are planning on. They have not done it. They are thinking of discontinue. Currently, it is there. Echo 360 is available. Oh, I see. Yeah.
Okay,
Oh,
Yeah, that threw me off the other day. We were in here working, and I looked at my phone and realized we were here an hour longer than I thought.
wait a second, this is the true time, right? What's the astronaut?
it's like my house, Prachi believes in not changing the time. And there are 5 clocks in the house, and each one is 15 minutes ahead, 14 minutes ahead, and no change of time during the
And then
daylight saving. So
Everything
I
else.
have to calculate. So I just don't look at that. So I just don't look at this. It's Prachi's time.
okay,
So I have to say something. I didn't make any. Remember, we sort of raised the problem last time. I don't think I have a result there, but I can talk a little more about that. But there was also this few comments I heard here and there that they want to go to geometry part of this more than doing the quantum mechanics. So maybe I should wind up with today. And there are 2 things I can do. I just talk about the diagram itself, which I don't have a complete result, but I can do more examples there and maybe think along that. Or I also, I had a lot of time, like Philip raised a point last time that when we say the limit on J was from J1 minus J2 to J1 plus J2, it was not satisfactory. At least there are comments being made that just because it works. So I can add on to that part. So that's one thing I have a concrete thing to say on. Or we can use a diagram which is more relevant to the discussion here in this group maybe. So what, any comments on that? Any suggestions?
maybe at the end, just 1 minute for once.
Okay, sure. So do the
1 minute.
do the Phillips argument better.
The equation.
Uh-huh. So only 1 minute for that.
That's 1 minute.
Rest everything on angular momentum.
What's the topic for today?
Oh yeah, I can.
I can
Yeah, I can
summarize a little bit about what we are trying to do here.
Yeah.
So when we are on this floor, we don't get chalks.
Oh.
I ran out of my chalk because people were stealing it from 356.
Really?
People stole every piece of chalk that I had in that room.
Oh.
All 5 sticks. Very sad. It's like
That is.
it's like $3 right there.
Stole it from you.
Entirely.
Gets it out of the frame.
That's good. So for Aryan, right? For Aryan, and is Harsha logged in by the way? He might log in from. Yes. Oh, he is. Okay. Hello, Harsha.
Hello from everybody.
Yeah, I'm here. Hello.
Okay, nice. Thank you.
Can you hear
Are you in the airport?
The airport? What? Sorry?
Oh, do you want your microphone?
Oh, I have. So are you at the airport?
Oh no. I'm still at home, but I think I'll have to start in about a half hour.
You have to work on the audio so that I don't think we can hear it.
Oh, okay.
Oh no, not Harsha. I was telling about our system. We're just
Mm.
experimenting. Yeah.
Like a Bluetooth speaker.
Yeah,
I have-
it's not clear, but I can hear you.
It's like it's specifically for meetings and conference calls, so it's like good for voice.
I went out the car, but
Okay. Okay. So for Aryan and Harsha and others, I think they all know. So this is a group that was started by Devjani and Jackson. They wanted to discuss ideas in quantum gravity. Of course, I think probably motivated from UREX interest in this. So they started reading a paper by Rovelli, if I'm pronouncing his name correct. Rovelli, and that in particular there is a diagram in their paper. If let's say position are I, right? So these are positions. If they do not commute, let's say, we are saying the space is, and that will immediately lead to space being discrete and so on. It's not a continuous space variable. Then we can think of a area element, which is usually described by a triangle. And this, if this is not zero, we can say that they're represented by angular momentum variables. That's where most of you will be able to connect. There is no need for this to be exactly the commutation relations for the space variables, only space, there is no time here at all. But if we say that is that's behaving like angular momentum, then we can think about an area element constituting 3 angular momentums, which requires that J1 plus J2 plus J3 is equal to 0. Immediately you can write that as J3 is equal to J1 plus J2. And that leads to the ideas of addition of angular momentum, which is sort of a textbook problem in physics. But there is a difference in the way we analyze things. Here we are saying that given J1 and J2, what are the states possible for J3? And here we are saying if there are 3 vectors, all 3 allowed, what are the states for all 3 possibilities? So the way we analyze it slightly different. If this is true, immediately what can be observed simultaneously is the Z component. So that's it. And the eigenvalues of this are M1 plus M2 plus M3 is equal to 0. So there are 3 vectors represented whose states are represented by, let's say, J1 comma M1, right? And J2 comma M2 and J3 comma M3. And these are all integers, J1, J2, J3, maybe say this better. So any one of that can have integer of or half integer values, and M for a given J can go from plus J to minus J, right? So that's the rules of the game. We have 3 J's. Each one of them can be half integer or integer. And accordingly, the M's can go for a given J, they can go from the highest to lowest. So, and all are integers, or this one is half integer. And because you want to satisfy M1 plus M2 plus M3, this boils down to J1 plus J2 plus J3 being an integer where n is equal to 0, 1, 2, and so on. So that's one relation. And the second one is M1 plus M2 plus M3 equal to 0. So instead of thinking in terms of addition of angular momentum, you think of these 2 conditions and what are the possible states. So that means to say an area element we are thinking of, what are its characteristics? We say typically that hydrogen, the moment we say hydrogen atom, there are the states we think about, like what are the possible states. Similarly, the moment you think of an area element, what are the possible values of J1, J2, J3 that are allowed, and what are the possible values M1, M2 plus M3. So that gives you some, you can say, structure for every tiny element of area that you can build space-time out of. Now, that's a problem I posed in my words. I don't know what quantum gravity really does, but there is a diagram we are trying to analyze. And the diagram is for, let's say, for let, right? Let. So I was allowed to do this at the end of the lecture. So this is the first part of the lecture. So let's J1 be equal to 2, J2 equal to 3/2, and J3 is equal to 5/2. Right, that could be 3 values of J, and it turns out that since this has to be an integer, either all 3 are full integers. By full means they're not half integers, or 2 of them has to be half integers. That's the way we can get a. That's a constraint we put. So that's why 2 half and 1, or they have to be all integers. Then immediately you can think of. I don't know whether this is a triangle or not. Like this is my version of it. This dotted lines means my addition to the diagram, what Rovelli draws. Given J1, the sides of this triangle, multiply this by 2. So that represents the sides. 2J2 will be 3, and 2J3 will be equal to 5, right? So these numbers immediately give you 3 sides of a triangle, and on those sides there is some structure. So this 4 means you can draw 4 points. So the goal here is to understand the diagram. I'm not claiming that I understand it. So, but I'm explaining how I can generate the diagram. So 4 here, 3 dots there, and 5 dots here. Right. And based on this, I also label the first side is opposite to A, second side is opposite to B. That's kind of the vertex of a triangle, A, B, and C. To get A, I add the 2 sides next to it, and then subtract the third one and divide by 2. So 5 plus 3 is 8, minus 4, 4, divide by 2, so that's 2. Right. B is 5 plus 4, 9, minus 3, 6, divide by 2, so that's 3. And do the same thing here, 4 plus 3, 7, minus 5, 2, that's equal to 1. What this means is that there has to be 3 points connecting the 2 sides connecting. So I'll draw it like this. Right. So, and 2 points around this vertex. So let me, if I can draw this better, and same thing here. Right. So that's the diagram we are trying to understand. So for Harsha and Aryan, like we want to understand this diagram and what is the relevance of this in quantum loop gravity in this group. So that's the best I can do. There might I've been thinking that this seems to be very similar to law of cosines. 2 sides add and then subtract. So maybe there is, but I have not made the connection yet.
Just 1 minute, I wanted.
Yes.
Now?
Yes, please. Oh, you wanted the 1 minute. Oh, I thought I am allowed to have 1 minute.
No,
Oh, so, okay. Here. You need the.
No. This is there's a triangle, and you know here. I think it's very similar to your picture.
But otherwise.
You just shove it in your pocket if you want to.
Subtract the 10 seconds and go over this.
No, you can take the whole election.
No, this is it. Look, this is R1, because this is a circle around this. This is R2, and this is another circle, bigger maybe, R3, okay? This is A, doesn't refer to your numbers, okay? B and C. So notice that A is R1 plus R2, B is R2 plus R3, and C is R3 plus R1, right? And then you want to rewrite it. What is R1? What is R2? What is R3? You're getting those, it's A plus B minus C over 2. So that's the picture, geometric picture for it somehow. Okay? So let's say you started with the 3 circles. And you know these R's. What are the distances? So this is the relation. There must be something here. So what you drew here is, in a sense, okay, you're drawing a circle around this. You want them to be just tangent, so you can pick up this one, you see? And here, if you think about those dots as like inches, it will be this one. So something to think about and find it a little better. Okay, thank you.
Geometry.
So that's how it is related to Apollonian disks, you know.
Two of them.
I tried with other examples too. I can do one more example.
Okay. I think it works.
You see connection with Apollonian?
Yeah, that seems to be exactly Apollonian. So very right time for me to.
Thank you.
Like next lectures are yours.
Have you looked at like the angle, like the correlation between the angle?
No, I haven't. So, and literally, I mean, I really started yesterday night. Since then, you think about it, but I really did not work. I was very biased that it might come up in the way we were doing last time, M1 plus M2 plus M3. I was really biased in that direction, so I tried a lot. And then I was working on Philip's suggestion that, oh, what is the proof for that? So this one
It didn't
is
really
less.
click until you drew it like that.
Yeah. Seems like, and again, UREC does Apollonian geometry, so that's inbuilt in those. So I think it is there. But let me do one more example, just since we are doing this. Let's say there is one more you can build, which is 7/2, right? That's striking in the sense. So J2, now we can be very efficient about this. So J3 is equal to 7/2. Older students are not listening. Yeah. I just thought we will do a couple of more examples very quick now that we are very efficient at this. Like now I'll draw this as a triangle if you don't mind, right? And this is going to be A, B, C. This is 2J1 is 4, 2J2 is 3, 2J3 is 7, right? 4 dots here, 7 dots here, 4, 5, not space, right? And here only, 3, right? So 1, 2, 3. Since notice 4 and 3, if you do calculations, 7 plus 3, 10 minus 4, so that's 3, I suppose, correct? 7 plus 4, 11, 11 minus 3, 8, and that's 4, and this should come out to be 0. So notice all the lines are going this way. So no property, and this makes sense in the sense J1 plus J2, J3, if you draw it as vectors, so these are really collinear. So this is J1, this is J2, and J3 is coming back. So when the collinear vectors, it seems like a triangle is pretty much squashed into a line. So this vertex probably loses. That's just, I feel it is okay. It's consistent, but I might be missing completely. Just to give you another example, which is slightly. J3 is equal to 5/2, right? And again, yeah. Oh, sorry, I meant 3 is done half, right? No, 5/2 we did, 7/2, 3 half, let's say. Because half would be exactly like this, it will be collinear because it's extreme version. So half will be slightly richer. 2J1 is again 4. 2J2 is 3. 2J3 is equal to 3 again, right? Yeah, 3. ABC, so 3 plus 3, 6 minus 4, 2 equal to 1. B is equal to 7 minus 3, 4, 2. And C is equal to 7 minus, so it's the same. 1, 2, 3, 4. 1, 2, 3. So 2 lines. Right, it sort of works, right? Always the number of lines connecting the two sides is the property of a vertex. One could imagine, like the way I was thinking about, which might be easier if you have the Apollonian rules. What are the next things that can come in? I started thinking about field lines. Can this go in a circle? Right? Then, oh, that's what. Yeah, no, but I was thinking that will depend on the property of the next element. So is the vertex really having a curl or not around it? So those are the things that come to my mind, but one has to really put in properties of space-time in there.
Should it be that the sides of, so say we're to form like a tetrahedron out of this, should the vertices agree with each other?
Probably there will be more constraints. That's what you're saying. Yeah, that's what the next adjacent ones will decide that, and I don't have at this point how to proceed.
If that were the case, that's interesting because that really restricts the structure of space-time in this.
Yes.
Interesting.
But one would think that this is all written down by someone, like people must have thought about this at least. So we just don't have the correct literature to refer to. So these are, I don't know again, these are called intertwiners in the reference that I am using. But that's all, that's half a page of work, and I really did not go around searching for the correct literature. So my limitation.
Intertwiners refer to the fact, like, the fact that, like, kind of the way the Apollonian gas is for like spin network, that how spin networks are kind of applied area.
That seems to be the suggestion. Yeah, they do talk about tetrahedron there, but I'm not able to see the connection there, except for the very broad, vague idea that area elements have to combine and so on. But I'm really not able to proceed further.
Correct me if I'm wrong, but that's kind of like
Yes.
Quantization of area.
Spin foam comes from the volumization of this.
Like this is area, and the foam comes from volume.
Yeah. I'm looking at it. Each tetrahedron can only have 6 defined values for the 6 vertices. And those would have to correspond to more tetrahedrons together.
Yeah. So that's the statement of the problem for Aryan and Harsha. But for the whole semester, I'll argue that we were doing quantum mechanics of angular momentum. That's all. But I think, yeah, that's what we were doing.
So again, when majority of J1, J2, J3, yes. So they are truly just by analogy.
Yeah, from what I can gather, what I can gather is that there are many reasons for space to be quantized. So you start with 3, you say that this is non-committed. You say this is non-committed, but then you have to immediately say what is the algebra for that non-commutation, and you can give whatever you want. One thing is that, oh, why not use angular momentum because it's so powerful there. That's it. It's just a reasonably arbitrary, I would say. But I don't want to claim anything because I haven't read the literature. But to me, it seems like it is reasonably arbitrary. Associate R to, I think, you basically write it as a, if this is I, one way to do this would be, I guess, sigma A B I. Right? That's one way of pretty much put a matrix to that. You could have chosen any algebra you want, but probably they have motivations to why it should be angular momentum. And from that point on, then I think ideas are all there between all of us, especially to you. Okay, all right. Okay, so we go back to angular momentum addition then, and so we'll go back to this structure, which I feel is sort of misleading in the classification sense here, but nevertheless, there are this addition of angular momentum laws that can be used. It's called CJ symbols and all. But again, I'm going to talk about elementary things about counting of states, which Philip pointed out was kind of interesting. So I felt I should look up. So I looked up, and it is not my work. Yeah, I think it should be useful. Okay, so we are going to say there is angular momentum. So that is J is going to represent angular momentum, which we already, it is it's given by it's described by a vector, but since it is quantum mechanical in the sense that Ji, the three components do not commute, the main conclusion is that you cannot observe all the properties of this vector, in the sense that you can measure the length if you want, which is given by, so if you measure the length of this vector, that's one observation you can make, and it comes out to be J times J plus 1, where J is integer or half integer. And again, that is a separate proof as to why that should be the case. After that, you still have a choice of measuring one component. You would like to measure three components of a vector. Classically, that's what we do. But in quantum mechanics, you are restricted to only one, because the moment you measure the next one, it will disturb the first one. So at the same time, you cannot do. Yes, yes. No, this has angular momentum has the units of h bar. Yeah, so yeah, so this is how you would write this. J times J will be h bar square. So this is how usually you write it. But then what happened is that I was myself misled. I was thinking that this has to do what we are doing, or if you think of it like this, so this is your vector J, and you can measure J1Z is here, right? And you're talking about triangles of this kind. If I'm adding two vectors, I can build like this. And I started thinking that, oh, this is integer, J1, J2, J3. And if these are all integers, that's a very well-studied topic, integer triangles, right? And then I was thinking, why has no one talked about connection between angular momentum and integers? I started searching, and I felt, no, it cannot be that far. So then my conclusion is that they're not really integer-sided because of this issue. So I think the connection is not there, but probably there is something along that line, but these are not integer triangles. So that's why I started writing it like this, because I was getting misled with the fact that J is the sides of J is not the length of the vector. Length of the vector is J times J plus 1 and the square root. That's not really integer. Right? So maybe, yeah, so maybe. Triangular. So yeah, I don't know that. So yeah, I mean, at least immediately I don't know that what are the implications, but I understand what you mean. Yeah, maybe sometime you should. Yeah. Okay. So we are talking about our vectors which have a length like this, and one of its component is going to be h bar times m, where m is allowed to take plus j, and then j minus 1 and minus j. So that's clear, right? If j was 3, 3, 2, 1, 0 until minus 3, and if it was plus half, then it is only two states. Okay, so that's the definition of angular momentum itself, but we want to talk about this is called composite angular momentum. You add two angular momentums. And I should say that when we say the z component, that is a frame we have chosen. At the moment we are talking about z component, there is a frame we have chosen, that a direction of the axis has been, at least the z direction of the axis is fixed. So we are talking in a reference frame here that plays a crucial role. So all three vectors have that same reference. We cannot keep changing. For J1, you change it, J2, so you all three have the same reference frame, and each of them have states J1 and J2. So we will represent now. Now the question is, J1 of course is J1 comma M1. Again, notice we are saying that if we are talking about angular momentum, these are states that define that space. It is like saying unit vectors. Is that clear? Maybe I should clarify that a minute. So any vector that is represented by angular momentum, the completeness relation will be 1. Let me write it as one whole, sometimes even as two vectors, but there are no vectors here. So this is 1 if you want. That is equal to sum over all m's. So this is a completeness for a given j. So if I fix my length of the vector, what are the possible z components I can have? What are the possible things I can measure? If I measure, what are the outcomes it can give? Then the states possible are j comma m times j comma m. And m can run from minus j to plus j. This is equivalent to if I'm in two-dimensional real space. I like to write this this way. J hat is equal to 1. Is that a familiar? I think this is like an outer product, right? So this is the equivalent thing. So for example, if I say this was 1, 1, 2, 2, this is summation over m going from let's say E1. Sorry, EI. That reasonable? That's the completeness relation I'm using in here. If I'm interested in the dimension of this space, so this will be a subspace in the all possible j. So for a fixed j, if I take the trace of 1 for the given j, this will come out to be, since it's a trace, I can put it on the other side. So this will be m going from minus j to plus j. So since it's a trace, I'll put it on the other side, right? Is that? Did I mess up? Yeah, I think this is just this correct, right? Because I would put a dot product here, right? That is what I will do. So, and I'm using the trace property to put the column vector to a row vector on the other side. This is equal to delta mm. They're saying they are orthogonal vectors, so they're all input to this, and that's nothing but 2j plus 1, I suppose, right? Yeah, because there's a yeah. If it is half integer, that should also come out. Yeah, right. Is that obvious? I guess, right? Yeah. Okay. So that's what usually you say this is a counting argument, but it is basically the trace of this quantity. Before I go into the yeah.
J plus 1.
Yes. Yeah, that's all, yeah. But I'm going to use this idea, exactly same idea, to do something about the counting of two different bases and say that they have the same state. So we have this piece here. But while we are here in this simpler picture, let me also do one more thing. Let's talk about a rotation. Remember, I have an axis here, and what will happen to the angular momentum if I rotate the axis about the z-axis by an angle phi. So rotate about z-axis by, let's say, delta phi, small infinitesimal rotation, and that operator is given by, so small change is equal to, let's say, I times delta phi times jz. This just means that the angular momentum is a generator of rotation. That is all it means. Is that okay? We did this a lot in more explicit ways earlier, but a simpler way of looking at it is that a total u would be 1 plus I delta phi jz. This is a sort of a poor man's argument, not going through the full algebra that we did 2-3 weeks back. But a simple argument would be, if you do this multiple times, right, you should get your full rotation. So u of phi would be equal to, I do this infinite, it's like adding area under a function, right? But I do this phi over delta phi. So n times you do the same rotation. The restriction here is that we are taking the limit delta phi tends to 0, so that 1 over delta phi tends to infinity in such a way that delta phi over delta phi is actually equal to 1. Right? So those restrictions are needed. And if that is the case, this is nothing but I can take this phi and do this, right? This is an exponential, right? Exponential of I jz raised to phi, and that's e raised to I phi j. But that's not very relevant. The main idea is that if I have this operator, it is an angular. It represents a rotation about z-axis, which is if you have done quantum mechanics, it's very common. If not, this is a motivation for that, a simple hand waving argument. But you can go through the details in a lot more details and get the same idea. But this is harder if it is having two axes. That's the main thing. If it's one axis, I think there's nothing wrong in it. If you first rotate about z-axis, then y-axis, and then come back, if you do it multiple times, then these don't commute, and that's not so easy to do that in this way of doing. Reasonable? Right. Okay, so if that is the case, then if that's an operator, so u of phi is exponential of this, I can say what is the trace of this operator. And let's also say that this is in the J space. While the angular momentum is in this J space, you have this 2J plus 1 coming in. But if this is an operator, think of a matrix. We are all used to thinking of it as a matrix. In that subspace of J, what will this be equal to? That's what we are saying. If there is so remember, trace of a matrix M is the same as, let me write this as, just for simplicity, if it is like this, then I would say this is trace of 1 times M times 1. So this has to be completeness relation. I'll fill this in. So this is trace of trace can go in, and I have this dot product here, right? Let's say this is M, and there is a summation over N, or let's say M prime. Right. So this is M, this is M prime, and since there is a trace, this will automatically bring this vector to that, right? That is at least that's the way I look at it. But this is completeness relation. So this is EI So this is EM now, EM hat dotted with M, and then dotted with EM prime, and again this is dotted with this because of the trace. That is how you would do the trace. We want to do that here, but now our completeness relation will be dictated by this. That's the main idea. So I'm not going to do this. I will literally do this, but this is what I'm going to essentially do. Any questions here on this? Right. Okay. So this is equal to put this. So this is trace of, I can put a 1. So this is summation over M times J comma M, J comma M, e raised to I phi J Z, and then I have J comma M prime, J comma M prime. So we are 50 already. We can go slow, or should I be hurrying? So is there a time limit? The final weeks, everyone is. Oh, okay. Okay. So that's your completeness. Trace allows you to move this on the other side. That's the same as, and this should run from minus J to plus J. And M prime. I left space here, but then I did not write it. M prime. Thank you. Right. Thank you. So this one is for this, and that one's for that, and the trace can allows me to bring that on the other side. So this is M equal to minus J plus J M prime minus J plus J, and this is J M. This is an eigenvector of JZ, so that replaces that with I M prime phi. It's the only thing that happens, and this is J M prime. When I bring, let me write that down, M prime and J M. This is nothing but delta M prime. They're orthogonal sets. This can come out now. This is a number. So this is essentially M equal to minus J to plus J M prime e raised to I M phi. This is again delta M prime, delta M prime. One of the summation can be done. It basically allows this to survive only when M is the same as M. That's what it is. So this is equal. M is equal to minus J plus J E I M phi times delta of M. But that's always equal to 1, right? For every value of M, this is equal to 1. Kronecker delta survives. So we are doing summation of exponential I phi. So trace of U is equal to M e raised to I M phi. Sum this up, right? So this is, I'll start from the top instead of the bottom. That's I J phi. Right? So that's 1. Next one is go down, minus I phi. Right? Plus I can keep going. What is the last term in there? I have to get minus J. So I should do minus 2 I J. Right? If you're in engineering and J is a complex number, so that's really confusing. Or even quaternions, right? So I and J, but hopefully the context tells it away. Yeah. No. Yeah. No, it's not. Okay, so but I want to evaluate this. So instead of doing this, what I do is I subtract. So I'm going to lift off this limit. So I say I don't stop it here. I keep adding all the terms till infinity, right? But I have to subtract all this. So that's the subtraction. So it is minus. The next term would be, I've added one more to this. So it is minus I 2J plus 1 phi. And then the same thing again. Going all the way to infinity. Right, that's just a trick. It should have gone only till here, but I added them, subtracted them, right? So,
I think it's
yeah, that is okay. So that's a tricky part, actually. Yeah, good point. Because these magnitudes are really one. Like these are on the circle.
Why not just take positive? You want to get cosine?
Yeah, fine. Yeah.
Just take plus and minus, get those stuff.
Yeah, actually, yeah, good point. Good point. Yeah. So this is,
One,
yeah, good point. Yeah. Okay. So let's fix this.
that was 0.
Yeah. So this is a geometric progression, finite, not infinite, right? So this is equal to exponential of ij phi times 1 minus e raised to, yeah. I think that's good enough. So that saves me. Okay? So then that is having no issues with, because otherwise the magnitude was really 1, so it is not really allowed. Agreed. So okay, now there is no issues. I think the argument there was that for so 1 plus x squared. So this is geometric progression, right? X raised to n. If you want this all going all the way to infinity, this is equal to 1 over 1 minus x, only if x is less than 1. And these are exponentials, which are really having our complex numbers. They are really on the circle. So that's not strictly true. Yeah. Okay. But now we are good because it's finite.
There's another thing, right?
Hmm?
Some different optics when you're adding weights.
Yeah, you're saying when we, I think, correct, exactly, or a single slit even, right? Single slit, you say that each one of this is a source, and you get exactly the same faces around to that. That's correct. Yeah, pretty much the same. Yeah, and the expression will be identical. Of course, it has to. So this is equal to, I multiply by e raised to I phi by 2, just mathematical, correct? So this becomes exponential of ij plus half phi minus of exponential of minus goes away, and probably this is, I'm just writing it because I know, but I think minus ij, because this 2 gives you minus, and then and this is minus, correct? No, help me. So this is minus ij, I got that.
Minus j plus a half.
Did I write this
Pull out
ex-
a minus.
So I wrote it
J
wrong
minus.
then. Is this correct?
Don't you think the first term is e to the negative ij?
This one?
Like the.
Oh, this, and this one should be, okay, what is 1 plus x squared plus x raised to n? One more to that, right? I think, yeah, so it is 1 minus x raised to n plus 1, is it? Is that what it is? I can add and subtract. So if you allow me to add and subtract, I can check this, right? So this is the same as 1 plus x plus so on. So I have infinitely added that. Then I have to subtract x raised to n plus 1. Yeah, x raised to n plus 1 times 1 plus x plus so on, right? Because I added, so this was x raised to n. And now I'm adding all this and I'm subtracting the next. So this one is 1 minus x raised to n plus 1 times 1 plus. Yeah. Okay, I wrote the formula wrong. Okay.
And it has one.
Huh?
N plus one terms.
Yes, yes, exactly. So that is the reason why we are getting the n plus one. But you agree that this should be the next term, right? Okay. Okay. Good. So then, so that should be written as minus I 2j plus 1 phi. Right. And then I think this works out. So minus ij, and then there is a minus 1 plus half. That works out. Okay. Better. Okay. So this is a cheat, but adding infinities and subtracting. Half the time it works. Okay. So, and there is one more. So this is e raised to I pi by 2, e raised to minus I pi by 2, right? That's the same as sine of j plus half pi times sine of pi by 2. That's what I think Urek was saying. This shows up in scattering or diffraction of a slit. But what we want to now realize is that trace of 1 is this. So I'm just going to copy that down here. The trace of exponential of I phi jz in that j space is equal to sine of j plus half phi. So that's just a knowledge if we want. If this is again a subspace, an operator, think of a matrix or some operator in a subspace of J, it turns out to be this, and this turns out to be 2J plus 1. And Philip, the way we are now going to create two complete relations in the same space, and counting means this. So now I'll give a small additional feature there. We can do this also. In the two spaces, it comes out the same. That's an indication that, okay, there is something more validation to that fact. So that's cool. That's what I'm going to do. So let me phrase the problem again. Any questions until now here? Because I'm going to erase this part. Questions? Okay. Harsha, is this all? Are you able to follow? Harsha is here. Why is he here? So he's in the campus? Yeah. Not immediately here. Okay. So now the so statement of the problem. So when you're having two vectors equal to the third, J1 plus J2, like J1 is a angular momentum, so J and M, that is a basis that supports that integer and the half integer and M accordingly changing. Same thing for 2. And then the question is, what about third one? What is a set, or what are the vectors or the basis that will span the whole set? So the easiest is a out product. So easiest one, we will call this product eigenbasis. This is like saying that we have a plane which is often the R1 maybe, right? This is the I and J. And we call it I1 and J1. And there is another plane which is R2, I2, J2. Then if a vector lies in both, like half of the vector lies in both, then you would say it's 4 vectors. Let's multiply them. That's the simplest in a sense. An outer product, you can call it an outer product. That's what we're talking about. The J1 has a space, J2 lives in another space. They commute in the sense that there is no coupling between them. They're really independent, but they have the same reference. So there is a Z component that is a common use that. But technically speaking, it's just 2 vectors. So that means the total basis would be J1, M1, and J2, comma M2. So to show all this things together, I just have to write the completeness relation. So this is equal, let's say, sum over M1 going from minus J1 plus J1 and M2 going from minus J2 plus J2, and that's your one. That has to be one, J2. Is that clear in there? So this version extended two times, multiple times, composite. That's all. Sometimes I think here it won't be necessary. Sometimes it's good to emphasize that it's related to the first vector and the second, especially when we are doing some of them, the evaluating method. I won't. So this is the completeness relation in this scenario. The other possibility is that is there another way to do the count? I think maybe not go beyond the timing. This is called the sum eigenstates. I think so. Is there another word? Okay, and that one will be so this is J3 itself is a vector. So the J's and M's are allowed. So we will call that, you can say J3 or we just J, right? For a given J1 and J2, we ask what are the values allowed for J and M. Given these two, what are the possible values of J and what is the other context we were talking about J1, J2, J3, adding up what are the possible here we think. Given J1 and J2, what are the allowed values of J and M want to have the first. And it turns out that this is have to go from J will take all the values from J1 minus J2 order to J1 plus J2. So, and the question was why this is being addressed here is that why this number is why should be the bottom line. Well, one is that you can immediately count and say that they are the same. And only thing I'm going to add is that okay, I'll calculate another quantity and show that this way of adding it. Not just counting into the trace, will also work with a little more. Not really. Again, a completeness relation. So this is J1. This is given in a sense. That's why. Hold on. Given J1 and J2, what are the values? And they are F minus J. And this is also complete in the sense that you can either use this basis or this basis, like saying rectangular coordinates, polar coordinates, same plane, doesn't matter which you work. Which means to say that if I work in this basis, if I calculate these quantities, I should get the same number. When we were doing this, when we were saying counting of states, we're actually just calculating the trace of an identity. The only thing I'm going to do is that instead of an identity, take the trace of another matrix. Oops, that's the problem. Okay, and just to give you an idea of where these vectors lie, let me describe this for J1 is equal to 1 and J2 is equal to 3 half. So J1 equal to 1, and I'm going to, so since J1 is fixed now, I don't have to write this. So if you allow me, I'll skip this writing. So the basis would be 1, 3 by 2, 1, and I'm going to write it in in a certain form. So I pull this down, 0, right, this. Second, one box. What I did was, this is one state possible, like this is multiplication of these two. And I reduce this, increase the second one, and 1 plus M2 here. It is 1 plus 3 by 2, 5 by 2. And 1 plus M2 here is 3 by 2. 1 plus 1 by 2, 0 plus. So this is kind of a diagrammatic way of seeing this, and this one will be minus. This here. This is half. I can also minus 1. I want to keep the 1 here the same. This, oh, this is fine. Next one, I would say this 0. So all I need. How many states here? 3. 2j plus 1, right? 3 times 3, 9. 3. This stops. This.
Mhm.
Next one will be, this
One.
one can be minus. And so this is minus half. So minus half, yes. This one now, this one again, right? So yeah, 1 time minus. Zero. Okay, and there is one more go down. So this should sit below this minus 1. Well, right, 4 into 3, 12. Yes, so there is one more line there. So because 3 half, right? Minus 3 half.
Wouldn't it just be symmetric at the half?
By symmetric, you mean if I switch the other one? So like this, if I draw a line?
Yeah, like these two signs.
Yeah. So, but they're still independent.
Right, yeah, but it would
Yeah.
just be the same
Yeah.
as those 6, but every time.
So you're saying that it's symmetric along here. This.
So like your
Yeah,
negative.
or
5
maybe
halves-
this line. You're saying. Yeah, I agree. So let me. Okay, if you allow me, so I think there is a box I'm making. One, two, three, four, five, six, 7, 8, 9. Yeah, collect. This was here.
I actually made something very similar last week, but in like a Cayley table diagram I have here. And then the
Oh.
the off diagonals give you allowed states.
Okay, yeah. Problem, I mean, these are all have some combinatorial level of arguments. But, I mean, I couldn't write it, my goal was to write it, but this is the product eigenbase, very easy. And the table here also goes with half minus half, and then goes to minus 3, 9, and 5. So this is the I have 3 by 2, 1 by 2, minus half, minus 3 half, minus 5 half. Here comes. Right, so that's and this is key because M1 plus M2 is the labeling eigenvector. Now the key is how do we see this in terms of this? What is the connection between sum? And then remember J can go from J1 minus. So I just draw the diagram here. Remember J can now go from J1 minus J2 because the 3 by 2 is larger. Can go to 3 by 2 and 3 by 2 plus 1 is 5 by 2. That's the three values J can take. This is J1 minus J2. J2 minus J1. Okay. That's J1 plus J2. And for each J's, you can have allowed values of M's. So I'm going to write with the largest one. That's 5 by 2, 5 by 2. This is now the product state with only these two being drawn. Earlier, I was only showing this two. The J1 and J2 is fixed. So I'm going to write it with J and M. So that's 5 by 2, 5 by 2. What is M1 plus M2 is M3, right? M is equal to M1 plus M2. So there's only one state here with that. This has to be this one. So this is exactly equal to in the both the bases. Because there's only one piece. So that's one argument. And this is again M now. M equal to 5 by 2. But starting from 5 by 2, I can keep going. This is 5 by 2, this is J. This is J. This column is J 5 by 2. I can go 3 by 2, 5 by 2, 1 by 2, 5 by 2 minus half, 5 by 2 minus 3 half, 5 by 2 minus 5 half. Right, 1, 2, 3, we have got 5 out of 12. So these are all the states for this. And remember, M is equal to 5 by 2, this is 3 by 2, these are the rows. I've got one of them, but there are two of them here. So that means I should be able to connect another one. But I'm already used a 5 by 2, so next I go to 3 by 2. This possible state is 3 by 2, 3 by 2. These are independent ones. Now I'm writing boxes so that I isolate. But the same value of M, so that means there are two vectors that you can use to build it. In the product basis, you would use these two. In the sum basis, you would use these two. And there is a linear combination between. That's all. And usually the club's got a coefficient goal of finding those. And there is an easy way of doing that, which Philip showed us how to do that, but I'm just doing it diagrammatically. That helps. But just to complete this or more, so this is 3 by 2. Once I start with 3 by 2, I can keep going. Three by 2 minus half 3 by 2, and I will stop here. So I have 5 plus 4, 9, 3 more. So this is the J equal to 3 half. No? But I have J equal to half also. That will fit in here. Half, 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 minus. And then that's it. That's your 15 states in a way of drawing it. Fit in here. which means that these two states are linear combination of these two. These three states are linear combination of these three. Right? Because these are half, right? M is M1 plus M2. These three states are linear combinations of these three. And the question is, how much is the numbers connecting them? These two are these two, this one is one. Right. So that's the connection between the vector, at least visually. One can go and get those linear combination numbers. That's what's called in coefficients, but I won't do that here. Here, my goal is just start from here and calculate the trace of this using the two bases. That's all I will. Questions? Oops. Okay. So now we want to use this diagram.
Can I see your microphone real quick? Make sure it's still on.
Out of battery. Yeah. I think if you give me 10 minutes, I should be able to. Is that? No. Oh, so then let's stop. No, let us stop and we'll continue this. Yeah, and yeah, and so yeah, if it is okay, I'll continue. But there is a popular thing that we should start talking about geometry here instead of. Okay.
Thank you.
Okay.
Is there any place in the literature place?
This thing? I'm pretty sure it's there. I mostly learn things from Schwinger's notes, but yesterday when I was looking at it, it's not there. Like I have done this all so many times and I was thinking, where is it? But it's, if you carefully read it, it's all there, but not the way, like there is no diagram like this. Yeah. Literally, I would think it is there. Yeah. Yeah. Okay. Ask them there.
Yeah, you can see there's two eigenbases, but it's not the two diagrams.
Okay. I think probably physicists take it for granted, or this is obvious. Do you see it like this? Maybe I should ask. Oh, you don't see it like that? Not.
It makes sense
Makes sense, yeah. But would you say it is too obvious?
for me.
Yeah, so see, that's the point. It's too obvious. Yeah, so like I asked them, how they decided on the.
Yeah, he's a Cubs fan.
Oh, really?
It's an American.
Oh. Cool.
So we're over.
We are getting recorded. Sorry, I mean,